Hello and welcome to our video on the derivative and the tangent line problem. This is the first section of chapter 2. The objectives for this video are 1, to find the slope of a tangent line to a curve at a given point. Number 2, use the limit definition to find the derivative of a function. And the third thing is to understand the relationship between differentiability and continuity. Let's start out by taking a look at the tangent line problem. In this, what you see in this case is in black, we have a function y equals f of x. That's this curve that I'm tracing right now with the laser pointer. In that case, whenever we talk about a curve does have a slope. Okay, and what we're going to do is we're going to try to estimate what that slope is, what the slope of the curve is. The slope of the curve is equal to the slope of the tangent line to that point. So in this case, I'm going to try to identify the slope of f at this point when x equals c. The coordinates of that point are c, comma, f of c. To do that, to estimate that, I'm going to go and I'm going to move off of c by a small amount, call it delta x. And so I'm going to go through, when I move off of c, I get to this x value, c plus delta x. And when I come up, I get this point, which is on the curve. And the coordinates of that point are c plus delta x and f of c plus delta x. The line in red that you see that connects those 2 points is called a secant line. And the slope of that secant line is, using the standard slope formula that you're familiar with, y2 minus y1 over x2 minus x1 becomes f of c plus delta x minus f of c all over c plus delta x minus c. And what happens then is, if I simplify that, I get f of c plus delta x minus f of c. The denominator will just simplify to be delta x. And the idea that we have here with this, as delta x gets smaller and smaller, gets closer to 0, this point right here is going to be moving closer and closer to the c f of c. And therefore the secant line, the line that connects the point with c f of c, where I'm at right now, that secant line is going to get closer and closer to a tangent line. So as delta x gets closer and closer to 0, the slope of that secant line is actually going to be closer and closer to the slope of the tangent line. And I'm hoping you recognize the limit process in this problem. With that limit process, I can now say that the slope of the tangent line, is equal to the limit as delta x approaches 0 of f of c plus delta x minus f of c all over delta x. That will give me the slope of the tangent line at x equals c. This now can lead us to what's called the definition of the derivative. The derivative of f at x is, what this notation is, f prime of x equals the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. That is, provided that limit exists. It is possible that the limit won't exist. Okay, remember, in terms of a limit, it exists only when I'm approaching the same value from the left as I am from the right. So again, the definition of the derivative, and you want to get this copied down, is f prime of x equals the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x, again, provided that limit exists. Now, there are numerous derivative notations, some that are common, some that are not so common. The ones that you see here, the first one, f prime of x, that's a very common one, and you'll see that notation. Okay, that one goes along also with the y prime. Both of those end up working out together, and you end up seeing both of those. The other one you see here is dy dx, and that's the dy over the dx. That's dy dx, so the derivative of y with respect to x. And that's kind of related to this other one, the fourth one here, d over dx of f of x. Those are two other very common notations for the derivative. You see both, okay? The last one here, d sub x y, that's the derivative of y with respect to x. That is one that quite honestly, I don't see very often. Now, when you look at these, there are two gentlemen that are credited really with the development of calculus, especially the differential calculus. And one of those is Sir Isaac Newton, and the other is a man by the name of Gottfried Leibniz. In terms of those, they developed calculus in different places, Newton in England, and Leibniz, I think, in France and Germany. I'm not sure. But they developed it in two different places, and while there was probably some contact between them, they really developed them in different ways. And so thus we see the different notation. The notation, the F prime, the prime notation that you see, that is Newton's notation. And the fractional dy dx, that is Leibniz's notation. We will use both of them. In some situations, Leibniz's notation is easier and more helpful to work with, and in others, Newton's notation is better. So you should be familiar with both of those types, the prime notation and the dy dx notation. At this point, make sure you do have that definition down. We are going to go on and do a look at a couple of examples on using that definition to find the derivative of a particular function. Also notice here that our derivative is a function of x as well. So we're not necessarily getting the specific slope at a point, but we are getting a derivative function when we use this definition. So let's move on, take a look at a couple examples. The first one we're going to work with here is we want to find dy dx for y equal to x cubed minus 5x. Okay, so what I have to do on this one, remember the definition of the derivative. It's going to be the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Well, remember, f of x plus delta x is found by just plugging x plus delta x in for the variable here. So when I apply the definition of the limit here, I will have the limit as delta x approaches 0 of x plus delta x to the third power minus 5 times x plus delta x minus f of x itself, which is the x cubed minus 5x over delta x. Now at this point, we have to go through and multiply everything out to simplify that numerator, because the numerator right now is a big mess. It's going to get messier, but that's okay, because good things will happen. Number one, when you're working with polynomials here, as you simplify that numerator, one of the things that can help you out is to realize that everything without a delta x is going to drop out of the numerator if you've done it correctly. So let's take a look what happens here. With the x plus delta x, that thing to the third power, I have two options. I can remember to go and take x plus delta x times x plus delta x times x plus delta x, or we can work with the binomial theorem or Pascal's triangle, and we find that when I take x plus delta x to the third power and I multiply that out, I will get x cubed plus 3x squared delta x plus 3x times delta x squared plus delta x cubed. Now I do have to now distribute the negative 5, so that will give me the minus 5x minus 5 delta x minus f of x. Now remember again, this minus sign has to be distributed to everything inside, so I get minus x cubed plus 5x all over delta x. So pause the video right now, make sure you have this copied down to this point. Okay, welcome back, and let's go through from here. Right now, what I do know, when I look at this, you'll notice that x cubed, I have an x cubed and a minus x cubed. So those x cubes do drop out. Another one I have a minus 5x and a plus 5x. So those will drop out as well. And what I'm going to be left with now then is 3x squared delta x plus 3x delta x squared plus delta x cubed minus 5 delta x over delta x. Now, because if you look up there in the numerator, everything without a delta x is gone. So I do have a common factor that I can pull out. So the next thing I'm going to do is I'm going to pull out that factor of delta x, And what you see in blue is what I'm going to have left, the 3x squared plus 3x delta x plus delta x squared minus 5. Just pull that common factor out. And at this point, now I also have another common factor I can get rid of, and that's the delta x's. That delta x and that delta x will cancel each other out. And so what I'm left with now is just taking the limit as delta x approaches 0 of 3x squared plus 3 delta x plus delta x squared minus 5. And as x goes to 0, I get that that is just going to be, or as delta x goes to 0, I get that's just going to end up equaling 3x squared minus 5. And therefore, I can now say that the derivative with respect to, derivative of y with respect to x is equal to 3x squared minus 5. Take a moment, pause the video, and make sure you're comfortable with all these calculations I just did. Because you'll be asked to do these calculations, repeat these calculations in other problems moving forward. Once you are comfortable with everything, then come back and we'll take a look at another example. Okay, welcome back. Now, let's go take a look at what happens when we're not dealing with a polynomial. The next one we're going to deal with here is going to be, we want to find y prime now, which is the same as dy dx though, for y equal to 1 over x. So now we're not dealing with a polynomial, we have a fraction. So again, what I'm going to do is set this up using the definition of the derivative. We know that y prime is going to equal the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. So in this case, for this particular problem, I know y prime will equal the limit as delta x approaches 0 of 1 over x plus delta x minus 1 over x all over delta x. Remember, f of x plus delta x is just going to be, you replace the x with the x plus delta x, so I'm going to get that 1 over x plus delta x. The next thing I have to do, because I have to go through and get this thing simplified, the next thing I'm going to need to do is just get a common denominator. In this case, my common denominator is just going to be the product of x plus delta x and x. So to do that, to get the common denominator for the things in the top of this fraction, I'm going to have to multiply the top and bottom of this first fraction of 1 over x plus delta x. I'll have to multiply that by x. And I'll have to multiply the top and bottom of this second one by x plus delta x. So I'll have that. And when I do that, I get that this thing is equal to the limit as delta x approaches 0 of x over x times x plus delta x minus x plus delta x over x times x plus delta x all over delta x. So we got a lot of delta x's and delta x's. So make sure you have everything straight with those. In this case, when I combine these into a single fraction, that numerator I've got to get it combined into a single fraction. That will equal the limit as delta x approaches 0 of x minus the quantity of x plus delta x. Remember to put parentheses around that numerator of that second fraction so that you remember that you have to subtract everything. That's going to be over x times x plus delta x, and that whole thing is still over delta x. When I go through, distribute that negative sign, that's going to be the limit as delta x approaches 0 of x minus delta x all over x times x plus delta x over delta x. Simplifying that further, the x's that you have here, these two x's will end up canceling each other out. And so what I'm going to be left with now is negative or opposite of delta x all over x times x plus delta x, and let me close that parenthesis off, all over delta x. And that, now remember, the other thing you have to remember here to help you out with this is that dividing by that delta x is the same as multiplying by 1 over delta x. So this thing can be thought of as the limit as delta x approaches 0 of the opposite of delta x over x times x plus delta x times 1 over delta x. And again, what happens here is these delta x's will cancel each other out. And I'm now left with the limit as delta x approaches 0 of -1 over x times x plus delta x. And as delta x goes to 0, this piece in the middle here, this in the parentheses, that's just going to be x. And so I'm going to get that equal to -1 over x squared, or therefore I can say y prime is equal to -1 over x to the second power. Again, please pause this video and make sure that you are comfortable with all the calculations that we did in terms of getting that common denominator, simplifying the fractions that we had in there, simplifying that whole complex fraction, and then to the point where we take the limit. So pause this video, make sure everything is comfortable. If you have any questions, please remember to write them down and ask them when we come to class next time. Welcome back. Now let's take a look at an alternate form for the derivative of a function. Apparently I can't spell derivative because it's spelled wrong, but it should be D-E-R-I-V-A-T-I-V-E. I missed an R. But what we have in that alternate form is that f prime of c. Now notice we're including c. What this does is this is how we can find the derivative at a particular x value. So we're not necessarily going through and using that x plus delta x, that definition, to find a derivative function and then use that derivative function to come up with the slope. We're actually saying I want the derivative at some particular value c. And so what I can do is I can set that up and say that the f prime of c is going to equal the limit as x approaches c of f of x minus f of c over x minus c. Let's look at an example here. What I have is I have f of x is x squared plus 5x minus 4, and I want to find f prime of -1. So in this case, c is -1. Now, the first thing I'm going to have to do, I have to identify what f of x is and f of -1, because since c is -1, and remember, in that definition, this alternate form, the numerator is f of x minus f of c. So in this case, I plug -1 in for x, and I will get that comes out to be -8. So I know f prime of -1 is going to equal the limit as x approaches -1 of f of x minus f of -1 all over x minus -1. And with the information I have and simplifying that, that's going to give me the limit as x approaches -1 of x squared plus 5x minus 4 minus the -8 over x plus 1. Simplifying that numerator, that's going to be the limit as x approaches -1 of x squared plus 5x plus 4 over x plus 1. Now here's the cool part. If you think back to synthetic division, when you worked with synthetic division, one of the things you should remember is that the remainder in synthetic division was also equal to the function's value at that point. And so by going and subtracting the function's value, we're actually eliminating the remainder. So this thing will always be able to factor. Whether you understand everything I just said there or not, just keep in mind that this numerator will always be able to factor, and one of its factors will always be what's in that denominator. There will be a common factor there. So in this case, I can factor that. I get that x squared plus 5x plus 4 over x plus 1 equals the limit as x approaches -1 of x plus 4 times x plus 1 over x plus 1. And again, you'll notice the common factor. The x plus 1s drop off. And so this is just going to be the limit as x approaches -1 of x plus 4. And plugging the -1 in, I get 3. So what I know on this case is I can say f prime of -1 is equal to 3. Or, in other words, the slope of the tangent line to this function f at x equals -1 is going to be 3. The last thing we have here is the idea that differentiability implies continuity. Okay? If a function is differentiable at x equals c, then the function is going to be continuous at x equals c. This is an important thing to keep in mind, that if you know that a derivative of a function at x equals 4 is equal to a number, then you know for sure that the function is continuous there. But you do need to go and note, please note, and put this in your notes, star it, make sure it stands out. This does not say that if a function is continuous at x equals c, then the function is differentiable at x equals c. That is definitely not the case. If the function is differentiable, I know it is continuous, but just because a function is continuous does not mean it's differentiable. For example, we have two functions graphed below. One is y equals the absolute value of x minus 2. What you need to remember on this case, the derivative is the slope of the curve or the slope of the tangent line. Well, in the absolute value of x minus 2, this graph is formed by two linear functions. This piece right here has a slope of -1, and this has a slope of +1. And since the derivative is a limit, the limit as I approach, in terms of the slopes of this thing, the limit of my slopes as I approach 2 from the left is going to be -1. The limit of my slopes as I approach 2 from the right is going to be +1. Well, in that situation right there, I'm approaching two different values. So since I'm approaching two different values, as x gets closer to 2, the slopes are, I know the derivative doesn't exist. The limit doesn't exist, and therefore the derivative doesn't. In this situation right here, with this absolute value symbol, what's occurring at 2 is called a cusp. Or sometimes our book even calls it just a sharp turn. Anytime you have a corner or a cusp, the derivative does not exist at that point. The other place that we have a derivative that doesn't exist is, and when it's still continuous, is at this graph where we have y equals x to the 1/3 power, or the cube root of x. In this case, the graph is going to be fairly level, and then it's going to get very steep, and it's going to be very steep and run right next to the y-axis, and then it's going to go off in this direction. Okay, so what happens here, as we are getting to at 0, at that point, we are getting a vertical tangent line, and because at a vertical tangent line, a vertical line doesn't have any slope, we would say that the derivative doesn't exist there. So anytime you have a vertical tangent line, the derivative doesn't exist. So in this case right here, we have a vertical, whoops, let me put a pen on. We have a vertical tangent line. And when I have a vertical tangent line, I know the derivative doesn't exist. This concludes our first video on the derivative. It is working with the definition of the derivative, so you should be comfortable. You should know both definitions, the f of x plus delta x version and the f prime of c version. So you should know both of those, and during class we will be working with both of them. And eventually, very soon, we will use these definitions to help us identify some basic rules that will make calculating derivatives a little bit easier. So make sure you're comfortable with everything here. Make sure you go back through if you need to look back at any of the questions or any of the examples. Also, remember to do the WISC, where, when, and where did you watch the video. Give me a summary of what was talked about in the video, and then indicate any questions that you still have on the video. And we will see you in class on, I think it's Thursday. So have a good evening, and we'll see you then.